Hello there, this is Dr. Staley again. Today we're talking about Chapter 8. This is the first lecture from there. The title of the chapter is Electron Configuration and Chemical Periodicity. Now, last time we talked about a couple of different things. We talked about the quantum number n for electrons in an orbital. How, n could equal 1, 2, 3, 4, etc. And how in the first layer of electron, and how these function as basically different layers of electrons, but they actually refer to how many half wavelengths of the electron de Broglie wavelength, how many half wavelengths can fit at each level. So at first, there's only one, and it's spherically shaped. For the second, there's 2, and just picture this as being like twice as large. I'm not going to draw it that way because I need space on the board. For 3, same deal, and for 4, where the outermost circle represents the edge of a sphere where 95% of the electron's wave function is. We could also kind of think of that as where the electron, if you picture the electron as a particle, where it spends 95% of its time. Now, at the second quantum number n, we get 3 different orientations of an orbital that looks very, very similar. So I'm just going to represent it with 1. I'm going to say times 3 of them. At n equals 3, we've got the same thing, except that in addition to having a node going through it that's flat, there's a second node going around here that's spherical. Times 3, and for n equals 4, same deal, except now we have 2 spherical nodes. Times 3. And then at the third level we get, the d orbitals. And there are 5 of them. Fourth, same deal, d orbitals, but then there's, a spherical node there. Each time we go up a level in one of these categories, it just adds a spherical node. And at the 4th level, we also get the f orbitals. And there are 7 of them that can fit in there. We talked about how there's the second quantum number, which I'm writing here as L. So the second quantum number is L. I'm writing it here as the cursive L, so it doesn't get mistaken for a 1. And L could either be 0, 1, 2, or 3. And then there is, of course, going down here, m sub L, where quantum number n is the electron layer that the electrons are in, L is the type of orbital that it's in. This is the this is the angular momentum. Then m sub L, going down this way, is the magnetic field generated by the angular momentum. Or, in other words, this is the type of orbital, this is which specific orbital in there. So m sub L can be anything from minus L to 0 to plus L. N has to be a whole number, 1, 2, 3, 4. L has to be a whole number, or 0, that is up to 1 less than n. So m sub L for the f orbitals could be anywhere from -3 to -2, 1, 0, 1, 2, or 3. For the d orbitals, -2, -1, 0, 1, 2. For these orbitals, it could be -1, 0, or 1. And for this, m sub L can only be 0. Now, we talked about these, and and then I jumped ahead just a little bit. So let's just section these off using a different color. And these here get sectioned off using a different color. There. And yeah, so this is also known as the s orbitals. Yes, these are also known as the s orbitals. These are also known as the p orbitals, the d orbitals, and the f orbitals. Now, at that point, I kind of jumped ahead a little bit, and I started talking about another quantum number. So we got n, l, and m sub L. This next quantum number is m sub s, the magnetic field associated with the spin on an electron, where it can be equal to either plus 1/2 or it can be equal to minus 1/2. And let's talk about this very briefly and what the implication is. So the spin on an electron comes from the fact that electrons have magnetic fields. Not only do they have electric fields, they also have magnetic fields. So that if you have an experiment where a beam of, let's say, hydrogen atoms, so these are not H2, these are just hydrogen atoms by themselves. So it's one proton there with one electron going around it. So if you have this beam of hydrogen atoms, and you have it go past a magnet, south, north, south, north, then what will happen is that this beam will actually split in half. And you can put some sort of detector on the other side and detect where the beam actually hits. Now, the reason for that is because the electrons, when they're by themselves, they act as though they are magnets, and for their size, they're pretty strong magnets. So that when the hydrogen atoms are coming in here and they enter this magnetic field, they switch to either point in the same direction of the magnetic field or in the opposite direction of the magnetic field. And that causes them to either be deflected down or be deflected up. Now, electric fields and magnetic fields are related by the fact that if you have one and you move it, then you will generate the other at a perpendicular angle. So if you have an electric field and you spin it, then you will generate a magnetic field that goes perpendicular to it according to the right-hand rule. So if it spins that way instead, then the magnetic field goes this way. And because these are magnetic field lines, they always there we go. Because these are magnetic field lines, they always connect with one another. Well, the fact that the electrons have these magnetic fields means that when they are put together in an atom, they attract each other as though they are, I don't want to say exactly as though they are bar magnets, but that is sort of the idea. Where, if you have two bar magnets, you can put them next to each other, and they have a very strong force pulling them, and the magnetic field is very, very strong, pulling them together. Well, electrons are kind of like that, except that electrons are also negatively charged. And that negative charge pushes them apart. So, as a result of this, what we get is the Pauli exclusion principle. Now, the Pauli exclusion principle is most often stated as no two electrons in the same atom can have the same quantum numbers. That's the way it's normally stated. So we've got the quantum numbers n, l, m sub l, and m sub s. And from a practical standpoint, what that means is that n is the number of the electron shell that the orbital is in, L is the type of orbital that the electron is in, m sub L is which specific orbital within that type the electron is in, which means that any two electrons that are in the same orbital have all three of these numbers the same. And they would be different from each other by this last one, the electronic spin, m sub s, where one electron would have m sub s as 1/2, the other would have m sub s as negative 1/2. So if we had a third electron in that same orbital, it would have all three of these the same because it's in the same orbital. And the spin, well, it would have to have the same spin as one of the first two. So, by the Pauli exclusion principle, we say no, we can't do that, that's not allowed. The more like physical reason why that's not allowed is because if you is because these two electrons that are spinning so close together that they're, we can think of them like bar magnets that are stuck together. The thing is that because electrons are so small and they're so close together here, they cancel out their magnetic fields cancel each other out, so that a third electron that's over here and is trying to come into that orbital would feel the repulsion, the electrostatic repulsion from these two electrons pushing it away, and it would not feel an attraction from their magnetic fields. So we only have the repulsive force, the arrows I put here pushing the thing away, and we would not have the attractive force, the two arrows I put here, pulling them together. Now, what that means is that, because each of these can only have two electrons in them, it essentially means that the electron orbitals fill up. And that has a major impact on another kind of, on another attraction. This attraction being the attraction between the nucleus and the electrons. Finish erasing that. So, in our model of the atom, we've got the nucleus, which has a charge of Z. Okay, this is, from the Bohr equation. And then we have the nucleus, which has a charge of Z, which, we get from the Bohr equation. So Z plus, because it's a positive charge. Z is the number of electrons is the number of protons in the nucleus. Then we've got, the first layer of electrons. We got the second layer of electrons. Got the third layer of electrons. Got the fourth layer of electrons. Now here we also have two competing forces. We've got the attraction between the electrons and the nucleus. And we've also got the repulsion that the electrons give to each other. This electrostatic repulsion has a name that's called either, we could call it electron-electron repulsion, we could call it the shielding effect, or we could call it the screening effect. And what it basically means is that the electrons in the higher energy orbitals feel the nucleus a lot less than the electrons in the lower energy orbitals. So we get Z, the number of protons in the nucleus, but Z is always greater than Z effective, which is the number of protons in the nucleus that an electron feels. Now, what this means is that the strength with which the nucleus binds the outer electrons is weaker than it binds the inner electrons, not just because the outer ones are farther away, but also because the outer ones are being repelled more. The strength with which the outer electrons are bound is partly due to this. And that ends up having a major impact on the energy levels within an atom. So I'm going to draw a chart here real quick. And it's going to look like the charts of internal energy that I've drawn in the past. But in this case, what we're thinking about is the internal energy just associated with one orbital and the one or two electrons that are in that orbital. So, here we go, we've got energy here, right? Now, in this orbital, this is the first orbital, n equals 1, L equals 0, so that's the 1s orbital. It's down here, and it has its energy level. Now, as we go up to the higher energy electrons, we get into the 2s orbital, and I just want to say this is not to scale. I need to leave room for myself for everything I need to draw in here. The electrons in the 2s orbital are significantly above the electrons in the 1s orbital. And so are the electrons in the 2p orbitals. But there's a key distinction between the 1s and between the 2s and the 2p's. A distinction which leads to the 2p orbital being significantly higher in energy than the 2s orbitals. 3 spaces because there are 3 p orbitals. And that difference is what we call penetration. Penetration is how we describe roughly how much of an electron's wave function is close to the nucleus. And here I'm going to draw a dividing line right there so that the text here and the text there don't get, aren't too close together. Now, with the s orbitals, there's a huge amount of electron density near the nucleus. Okay, we can picture this as the wave function, that is the electron that spreads out all throughout the cosmos, being the most dense near the nucleus. Or we could picture this as the electron, in its orbiting, spending the most time near the nucleus. We can picture it either way, they both work. But here with the p orbitals, the electrons spend most of their time away from the nucleus and only get close a little bit. So that the shielding effect is much stronger with the p orbitals than it is with the s orbitals, because the electrons in the p orbital spend more of their time away from the nucleus, and therefore there's more, and therefore they spend more of their time with the 1s electrons blocking their view of the nucleus. And so that shielding effect leads to a splitting in the electron shells. Now, as we go up in energy to the next level, we've got the 3s orbitals, and we've got the 3p orbitals, but then we also have the d orbitals. Now, the d orbitals, so penetration is important, but we tend to talk about this a bit more, so I'm just going to erase this because I need some more space. Now, the d orbitals have 4 lobes, and I actually haven't drawn them completely correct here. They have very, very little electron density near the nucleus, which is, at the center. There's the nucleus, there's the nucleus, there's the nucleus, 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 and nucleus. The d orbitals spend a lot less time near there. So the 3d orbitals, so the third level orbitals that are d, there are 5 of them. 1, 2, 3, 4, 5, 3d. They spend a lot of their time away from the nucleus and therefore have a lot of electron-electron repulsion. And that leads to an interesting phenomenon where once we get up to the 4s, that orbital is lower in energy than the 3d. Because even though the 4s has the right number of nodes to be in the 4th electron shell, the electrons that are in that orbital spend so much of their time near the nucleus as compared to the d orbitals that their energy level is lower. And the fact that their energy level is... And now, the splitting of the electronic shells in this way leads to what we call the subshells. So we've got electron shells and electron subshells, where the p electrons, the electrons there, these are all subshells. Now, I've been calling these types of orbitals. The more accurate term, and this is supposed to be 2p, the more accurate term is that these are subshells, not that they are, types. Because each atom has the same general structure with, a nucleus in the center and electrons going around it, because each atom has that same general structure, each atom also have orbitals that are the same general shape, that are the same general structure. And that leads to, a pattern here that can be memorized, where, come on, you. The energy of electrons in subshells goes, come on, you, there we go. The energy of the electrons in the subshells goes, S subshell has the least energy, the P subshell within any larger shell has more, D has more than that, and F has more than that. And at this point, we've reached the end of section 8.1. We're moving on to 8.2 now, and I can finally erase all of these orbitals that I've been drawing this whole time. Now, one of the things that, so I said that one of the things that comes out of the Pauli exclusion principle is that we can only have 2 electrons in any given orbital in any given atom. And the thing is that electrons don't just pick orbitals at random. They go into orbitals in order. Basically, any atom that is going to be stable is going to have all of its lower orbitals filled before its higher orbitals get filled. This is what we call the Bowel Principle. Aufbau is German because this whole concept was invented by German chemists. This is German for to build up. And what it means is that all atoms have the same orbitals. Now, because atoms have different numbers of protons and different numbers of electrons, the orbital shapes and sizes are not exactly technically the same, but they got the same geometry and the same general shape, so we're just going with this for right now. All atoms have the same orbitals, and we can picture electrons being put into those orbitals in order from lowest energy to highest. Now this is where the concept of, this is where the periods in the periodic table actually come from. When a given electron shell is filled and electrons start filling the next shell up, those new electrons go into orbitals that have the same geometry and the same general shape as the electrons in the lower orbitals. So that if you arrange the elements in such a way that let's say for example 3p orbital is being filled up directly below the 2p orbital, then what you get are atoms in line with each other that have the same configuration of electrons in their highest energy levels. But in order to do that, we need to talk about the actual configurations of electrons. So, according to the building up principle, we fill up the 1s orbital. If we have an atom, 2s, 2p, 3s. Now, if we have an atom with, say, 11 electrons, the electrons will go into the atom in the following order. This will get 2 electrons, this will get 2 electrons, these will each get 1 electrons, and then they'll each get their second, and then this will start getting 2. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We draw electrons as, I'm just going to put a big version here. We draw electrons as a half arrow going up or a half arrow going down. We have the arrows going up or down to remind ourselves that the electrons have a spin, and the spins of 2 electrons in the same orbital have to oppose each other in order for both electrons to fit in that orbital. We can think of it as a reminder that the electrons don't, we can think of it as a reminder that the electrons can only fit 2 to an orbital. This way we don't accidentally put 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So an atom that has 11 electrons has them filling orbitals in this configuration. And if we look at the periodic table, we'll notice that the atom that has 11 electrons in its ground state as a neutral atom is sodium. This is the reason why sodium is on the 3rd row of the periodic table and is the first one there. Now, for sodium, how do I put this? Well, sodium has reactivity, has chemical properties that are very similar to the atom that's right above it, lithium. So what is lithium's atomic number? Well, it's atomic number 3, which means it has 3 protons in the nucleus, and therefore it has 3 electrons in its electronic orbitals. So if we want to look at lithium, we're putting in 3 electrons. We start at the bottom and we build up. 1, 2, 3. It has 1 electron by itself in the 2s orbital, just like sodium has 1 electron by itself in the 3s orbital. So, two more examples of this. No, let's do one more example for right now. Let's say carbon. Energy of the electrons, 1s, 2s, 2p. And this is for carbon. Carbon has atomic number 6. Therefore, in its ground state, it has 6 electrons. So the electrons go in like this. 1, 2, 3, 4. And then the p orbitals start filling up. So here's the thing. The p orbitals can either fill up by having electrons pair up or by having electrons split apart. So either the magnetic force wins and the electrons are attracted enough to each other through the magnetic force that they pair up, or the electric force wins and they repel each other enough that they go into different orbitals. What always happens is that when the orbitals are close in energy, the electrons pair up. The electrons split apart and go into different orbitals. So we go 1, 2, 3, 4, 5, 6. Okay, fair enough. So this is where the electrons are in each of the atoms. But if we want to write out something as an electron configuration, this is not really a convenient way to do it. We don't really want to have to draw one of these graphs every single time. So we have a different way of writing out the electronic configuration that is simpler and easier. And that different way is, I'll get rid of this too. That different way is to, electronic configuration. We take this and we translate it to the format NL number. Where N is the number of the electron shell, L is the letter of the electron subshell, and the number is the number of electrons in that subshell. So if we were to write out the electronic configuration for sodium, we would write it out. So no. I'll use the other color for this. If we want to write that out, the way we would write that out for sodium is sodium, and we'd say that it has the electronic configuration 1s, and the 1s orbital has 2 electrons in it. So we write that as 1s2. Then we go up. The 2s orbital also has 2 electrons. 2s2. And then we go up. The 2p orbitals, there are 3 orbitals, and they're completely filled. So the 2p orbitals have a total of 6 electrons. So write that as 2p6. And our last electron is in our 3s orbital. So we write that as 3s1. Now that makes a whole lot more. Here, let me just include the sodium in there. Now, this way, this way of writing it out gets across the same information that this way of writing it out does, as long as you understand that s orbitals are lower energy than p orbitals, and that the electrons fill up the lower energy orbitals first. But it's also something, and so you can write that out with sodium. You could write that out with lithium also. So it's this one. So lithium that would become lithium. It has an electronic configuration 1s2 because the 1s orbital has 2 electrons in it. Then the 2s orbital has 1 electron, so 2s1. And then we can do the same thing for carbon. We write out carbon 1s2, 2s2, 2p2, 2s2, and the 2p orbital, it only has 2 electrons in it, so 2p2. Okay, so fair enough, so far so good. Now let me just, so now let's talk about a much, much larger atom. So let's say that we want to write out an electronic configuration for a significantly larger atom. Let's look at germanium. So the electronic structure for germanium is on the 4th period of the periodic table. So we've got our 1s electrons, our 2s electrons, our 2p electrons, 3s, 3p, 3d, then Down here, 4s fills up before that. Then the 4 P is up here. And technically speaking, on the fourth period, we do have the 4F subshell. But the 4F subshell is really, really high. 1, 2, 3, 4, 5, 6, 7. The 4F subshell is really super high in energy, so it takes a lot for it to fill up. So we don't normally bother with it. But what we're getting at is that when we use the Bowel principle to build up germanium's electronic configuration, we get this is taking a while. We get this. So this is a pretty big graph as compared to the others. And if we were to write out the whole configuration, then that whole configuration would be germanium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 3d10. Now, the 3d orbitals fill up after the 4s orbitals, so they're always written after the 4s orbitals. And then 4p, and there are 2. Now that is a lot. So wouldn't it be nice if there was a way that we could abbreviate that somehow? Well, it turns out that there is. And we do it using the noble gases. What's the configuration for helium? 1s2, nothing else. What's the configuration for neon? 1s2, 2s2, 2p6, and nothing else. For argon, it's all of these up to 3p6, which means that if we change this out for so let's do that for germanium. Now, the electronic configuration for argon is all of this, which means that because argon has all these orbitals filled, we could, if we wanted to, write germanium as in, so we write out argon here, 1s2, 2s2, 2p6, 3s2, 3p6. So we could, if we wanted to, say, well, germanium, write this out as germanium, has the same electronic configuration of argon, so we put argon in brackets, plus, and then we just write out the electrons that argon doesn't have. 4s2, 3d, 10, 4p2. So that by using the noble gases for all of the filled orbitals, we can take a really long electronic configuration and shorten it to something that's more useful. So here, I'm going to get rid of this. And I'm going to take this, I'm going to write it a bit lower. Wrong one. All right, so the electronic configuration for germanium is the same thing as for argon. Plus 4s2, 3d, 10, 4p2. Yeah, so having the argon there acts as an abbreviation. It means we've got all of the same electrons that argon has, plus we've got these extras. Now, the way that we go from the full configuration to the abbreviated configuration so full electronic configuration to abbreviated is we look at the noble gas that is one, you could say row, you could say period, above the atom in the periodic table, and use that. Now, the atom that's right next to germanium is gallium. There's on the periodic table, there's germanium here, then there's gallium right next to it. And on gallium, so if you wanted to, you could hypothetically have gallium here as an abbreviation and just have germanium is, gallium in brackets plus 4p1 because it's, one additional electron in the p orbital. You could hypothetically do that, but we normally don't because that's not useful for anything. And the reason that's not useful for anything is because the electrons in the highest energy orbitals have their own so we use that for this. That's because the electrons in the highest energy orbitals have their own name, which is that they're called the valence electrons. And sometimes d electrons are valence, sometimes they're not valence electrons. That gets complicated. But basically, the electrons that are in the highest energy orbitals, are the valence electrons, and the electrons in all of the orbitals below them are the core electrons. Valence is another way of saying bonding. These are the electrons that do the most to determine what an atom's chemical properties actually are. So by having our abbreviated configuration be like this, what we can say is, well, this atom has these core electrons, but honestly we don't care about those, so we're just going to pretend that those act like a noble gas. And it has these valence electrons that are really, really, this is what is usually going to be important to us. And so that's the reason why we have the abbreviation be this way. That's the reason why we look at the noble gas. The noble gases are they are noble. We call them noble gases because they don't react. Under extreme circumstances, they do react, but normally they don't undergo chemical reactions. And we will get into why a little bit later when we get into periodic trends in section 8.3. But for right now, let's just do a little bit of practice. Let's take these electronic configurations and let us give them the so let's take these electronic configurations and let us give them the abbreviated forms. Now, sodium, if you look above it on the periodic table, you will see that there's an atom that has this electronic structure, and that atom is neon. So sodium can be abbreviated as sodium, then in brackets, neon, and the last part, 3s1. Lithium, you look above it on the periodic table, it can be abbreviated lithium is helium 2s1. Carbon, if you look above it on the periodic table, the noble gas that's in the next level up, the next row up, is helium again. So we go carbon. I'm sorry, that was a little bit small. Lithium, helium, 2s1. Then down here, carbon, same deal, is helium, 2s2, 2p2. And here I'm going to make a point about carbon and germanium. Now, carbon and germanium have, so we've got carbon, abbreviated helium, 2s2, 2p2. Right below carbon is silicon, neon. Now, silicon has all the electronic configurations of neon, plus 3s2, 3p2, and we've got up here germanium, which is right below silicon. Has the core electrons of argon, then it has 4s2, 3d10, 4p2. For an atom like carbon, writing out the abbreviated electronic configuration doesn't actually save you that much space. In fact, I think it takes up more space. But it does allow you to see the similarity in electronic structure between carbon and the elements below it, silicon, germanium. I think the next one below it is tin. And that is that each of them have 4 electrons that are ready to bond in its highest orbitals. So with germanium, because the d orbital is complete, because the d subshell is completely filled, it becomes very, very non-reactive. Hypothetically, you could get it to react, but it takes a lot. So for germanium, the reactive electrons are the s electrons and the p electrons, and we can see the similarities here. Now we can say, oh, that leads to them having similar properties, and they do. CH4 has similar properties to SiH4 and similar to GeH4. Silicon and germanium can both be used to make semiconductor wafers. In fact, the first microprocessors were made using germanium as the main component instead of using silicon as the main component. That's because germanium was easier to work with, but we eventually switched to silicon because silicon is more common and therefore a lot cheaper. But in any case, writing out these electronic configurations allows us to see more easily where similar chemical properties, where similar reactivity in similar compounds and similar chemical properties come from in the periodic table. Oh, among other things, there are very few elements that can form molecules that are long chains. Carbon is, of course, famous for it, but silicon can also be used to form long chain molecules. Now, before we go, there is one last comment that I want to make about the building up principle and electronic configurations. And that is that as electrons fill orbitals, they don't always fill them in exactly the way that you might expect. So if we look at only the valence orbital in, let's do this here. If we look at only the valence orbital in calcium, scandium, titanium, vanadium, and chromium, if we look at only those valence orbitals, and this is the energy of the electrons in the various orbitals, if we look at only those orbitals, we end up seeing that the 4s and 1, 2, 3, 4, 5, 3d. With calcium, both electrons end up in the 4s orbital. With scandium, we've got 3 electrons to distribute. D. So they go 1, 2, 3. First two go in the 4s, the third one goes in the 3d orbital. Titanium, same deal. Got 4 electrons, first two go in 4s, next ones go in the 3d. And just as with the p orbitals, they start, putting 1 per orbital. 1, 2, 3, 4, 5. Just as with the just as with the p orbitals before, they start going 1 electron per orbital until they fill the whole thing up. And at that point they have to pair up. But there is an exception there for chromium and for the elements directly below chromium. And that exception is that because the electrons have the option of having 5 half-filled d orbitals and 1 half-filled s orbital, that's what they end up doing. Where in going from vanadium to chromium, the electron-electron repulsion momentarily, for that group of elements, the electron-electron repulsion is enough to overcome the attraction from the magnetic spins. And so the configuration for chromium is actually chromium, and the one directly above it is argon. (4s1) 3d5. Now, this is something that happens with the s and d orbitals. I'm not entirely certain about the f block. It might also happen with the s and f orbitals, but it happens with the s and d orbitals because since d orbitals are a high energy subshell from the previous shell, the difference in energy between this s orbital and these d orbitals is close enough that this becomes possible. And in rare cases, like I said, with chromium and the elements in its group, it actually does happen. It does not happen in the other elements to the groups to the right of chromium or the groups to the left of chromium, just with chromium in its group. So that concludes section 8.2. Next time we'll be on 8.3 and 8.4, and we'll finish chapter 8. Thank you much, and stay safe and stay healthy.